Welcome back. In this video, you'll learn how to find the area of surfaces of revolution with parametric equations. Let's get to it. Alright, so earlier in Calculus 2, you learned how to find the area of surfaces of revolution, which were formed by curves represented by functions in terms of x and y. But we can also find the area of surfaces of revolution formed by curves that are plane curves or parametric curves, which are represented with parametric equations. And so as a refresher, let's quickly review how we calculated area of surfaces of revolution in terms of x and y, and then we will adapt that to working in terms of t or any other parameter for parametric equations. So if you look at this graph right here, we have a curve represented in terms of x and y, right? This curve is represented by y equals capital F of x, and we have a particular section of that curve between two values of x that we want to revolve around either the x or y axis to form a surface of revolution. And so if we were to revolve this specific arc length, or this part of our curve right here, around the x-axis, we would form a surface of revolution that looks like this. As you rotate each point along this curve around the x-axis, you form this surface of revolution that has circular cross-sections. And the radius for each of those circles is this small r of x, which is the distance from the x-axis to the curve. And that is typically decided by that function capital F of x. And so when we wanted to calculate the area of a surface of revolution revolved around the x-axis, we used this formula. The surface area is equal to 2 pi times the integral from a to b, those are our two values of x that the curve lies between, of the radius in terms of x, times the square root of 1 plus the derivative of the function that represents that curve, squared, and then times dx. All right, and so this formula allowed us to calculate the area around this surface of revolution, which was formed by revolving this curve around the x-axis. But if we revolve this curve around the y-axis instead, we had a slightly different formula, because revolving this curve around the y-axis will most likely form a different surface of revolution. Right, so if we have the same curve, but instead of revolving around the x-axis, we revolve this around the y-axis, we will form a surface of revolution that looks like this. As we rotate each point along this curve around the y-axis, we will form a different surface of revolution that also has circular cross-sections, where the radius of those circles is the distance between the y-axis and the curve, which happens to be whatever value of x you are at along that curve. And so to calculate the area of this surface of revolution, we used a slightly different formula, that the area of the surface is equal to 2 pi times the integral from a to b, those same two values of x that the curve lies between, of the radius x times the square root of 1 plus f prime of x squared dx. All right, so both of these formulas allowed us to calculate the area of surfaces of revolution in terms of x and y for curves defined in terms of x and y that are either revolved around the y-axis or the x-axis. And so if we want to find the area of a surface of revolution for a curve represented with parametric equations instead, we're going to need a different formula. But in order to develop that formula, we need to remember how these two formulas were formed. Essentially, what these formulas are calculating is an infinite sum of the measurement around the circles that make up these surfaces of revolution. Right? Both of these surfaces of revolution have circular cross-sections, and so if we want to calculate the area around those surfaces, we just have to calculate the circumference around each of those circles and add them together for the length of the curve that is being revolved around the axis. All right, and so remember that the circumference of a circle is equal to 2 pi r. And so if we just take a look at our surface of revolution when we're revolving around the x-axis, the radius of our circles is small r of x. So we could replace r with r of x. So if I erase this, we'll have r of x. That would represent the circumference of any circle that is formed by revolving this curve around the x-axis. And then in order to find the area around the whole surface of revolution, we need to multiply the circumference of those circles by the length of this curve. And the arc length in terms of x and y is calculated using this formula. The arc length is equal to the integral from a to b of the square root of 1 plus the first derivative f prime of x squared dx. All right, and so the area of the surface of revolution would be equal to the circumference 2 pi times r of x times the arc length which is how we form this formula. We keep the 2 pi on the outside of the integral, but then the radius in terms of x becomes a part of this integral, which is how we get the integral from a to b of r of x times the square root of 1 plus the first derivative squared times dx. This whole integral, other than r of x, comes from the arc length formula. We just include r of x to then add up all the circumferences of the circles that make up the surface of revolution. All right, and then this same process could also be applied for our surface of revolution formed by revolving around the y-axis. The only thing that changes is the radius. Instead of r of x, we would just have x, and you would get this formula. But now that you are refreshed on where these formulas come from, we can now easily apply this to a curve represented with parametric equations to come up with new formulas to calculate the area of surfaces of revolution in terms of t, our parameter. And so let's look at these two graphs, but instead of working in terms of x and y, or instead of working with this curve as a function y equals capital F of x, let's imagine that this curve is instead a plane curve or parametric curve that can be represented with parametric equations. All right, so now this curve that we are working with is defined with these two parametric equations, x equals small f of t and y equals g of t. Both the x and y coordinates for the points along this curve are represented in terms of a parameter, t. And so we can use this same formula to calculate the area of the surface of revolution, but what's going to change is the radius. It's not going to be r of x anymore when revolving around the x-axis, and it's not just going to be x when revolving around the y-axis. So we can remove that radius, we can change that for each scenario. So I'm just going to represent that with r for now. That is our radius. We will need to determine that for each of these cases. And then the arc length formula is also going to change, right? We're not going to use that arc length formula in terms of x and y. We're going to use the arc length formula in terms of t, which we found in a previous lesson. The arc length of a curve between two specific values of t along a plane curve can be found by using this formula right here. The arc length is equal to the integral from some lower bound of t, t sub 1, to an upper bound of t, t sub 2, of the square root of dx dt squared. Dx dt is the derivative of the parametric equation for x. And then we add that to dy dt squared, where dy dt is the derivative of our parametric equation for y. And then, of course, we have dt because we're integrating with respect to t. And so that is going to replace L in this formula. And so now all we have to determine in each case is what that radius will be equal to. And so if we take a look at this surface of revolution first, where we revolve our curve around the x-axis, the radius will be the distance from the x-axis to the curve. And so that is this distance right here. But instead of being in terms of x, it is going to be in terms of t. And so what in terms of t will represent this distance? Well, remember, this curve is represented with these two parametric equations. One of them represents the x values, and one of them represents the y values. And so the distance from this curve to the x-axis is a value of y, right? It's going to be whatever value of y you are at along the curve. That will be the distance from the curve to the x-axis. And so that radius is just going to be what y is equal to, g of t. It's just going to be the function in terms of t that represents the y coordinates for the curve. And in the same way, for our surface of revolution that is formed by revolving around the y-axis, the radius, which is now the distance between the y-axis and the curve, is just a value of x, right? The distance from the y-axis to the curve is just whatever x value you are at along the curve. And the x values of this curve are determined by another function in terms of t, small f of t. So this radius is represented by small f of t. All right, and so we now know the radius for each of these scenarios where we are forming a surface of revolution by revolving a curve around the x-axis or the y-axis. And so now we can set up our formulas for calculating the area of those surfaces of revolution. So let's start with revolving around the x-axis. If we're revolving around the x-axis, the area of the surface of revolution will be equal to 2 pi, right? That's this part of the formula. And then we're going to introduce the integral from the arc length of that curve. And so we'll have the integral from t sub 1 to t sub 2 of the square root of dx dt squared plus dy dt squared times dt. And then we just need to remember to include the radius, which is also going to be in terms of t. In this case, it's represented by g of t, and you could also rewrite that with just y, and remember that y is represented by g of t. And so if you wanted to, you could write y in this integral, but I'm going to write g of t so that we remember that we're working in terms of t. And so now what we have right here is our integral, or is the formula that represents the area of this surface of revolution. We have 2 pi times the integral from t sub 1 to t sub 2 of our radius g of t times the square root of dx dt squared plus dy dt squared dt. And we're going to have this same exact formula for the area of the surface of revolution formed by revolving around the y-axis, except that radius g of t is going to become f of t. So around the y-axis, the area of the surface of revolution will be equal to 2 pi times the integral from t sub 1 to t sub 2 of f of t times the square root of dx dt squared plus dy dt squared dt. Okay, and so those are the two formulas that you need to know in order to calculate the area of a surface of revolution that is formed with a curve defined with parametric equations. All right, and that's all provided that the curve that we are using to form that surface of revolution is a smooth curve, meaning that it has no gaps or sharp points, and that the curve does not intersect itself. All right, and so to summarize what we just found, the area of surfaces of revolution in parametric form is represented by these two formulas, or these two integrals. If you're revolving around the x-axis, this is the formula you use. The area is equal to 2 pi times the integral from t sub 1 to t sub 2 of your radius g of t times the square root of dx dt squared plus dy dt squared times dt. And then when you revolve around the y-axis, you have the same formula, except that radius is now small f of t. All right, so g of t is just your equation for y from your parametric equations, and small f of t is just your equation for x from your parametric equations. Okay, so if you revolve around the x-axis, you use the equation for y, and if you revolve around the y-axis, you use the equation for x. So now that we have these formulas, or now that we have these integrals, let's look at some examples of finding the area of surfaces of revolution formed by revolving curves around an axis that is defined with parametric equations. All right, so here's our first example. We want to find the area of the surface formed by revolving the curve represented by the parametric equations around the x-axis. All right, so our parametric equations are x equals t squared plus 3 and y equals 6t, and it looks like that we are revolving the curve represented by these parametric equations around the x-axis between these two values of t, from t equals 0 to t equals 1. All right, so it's important to identify what axis you are revolving around. In this case, it is the x-axis, and I have it colored differently here to really highlight that. You need to make sure you know what axis you are revolving around, because depending on which axis you're revolving around, the formula changes slightly because the radius will be different. And so here's our formula for calculating the area of this surface of revolution formed by revolving the curve around the x-axis. Our radius is going to be g of t, which is what y is equal to in terms of t. And so let's work on setting up this formula. Like I just pointed out, we already have g of t. G of t is whatever y is equal to, which is 6t. So I'm going to write that on the side here. G of t is equal to 6t. But now we also need dx dt and dy dt in order to set up this formula. And dx dt is the derivative of x with respect to t, and dy dt is the derivative of y with respect to t. And so let's take our derivatives. Let's start with dx dt. Dx dt is equal to the derivative of t squared plus 3. Using the power rule for derivatives on this term, we will get 2t, right? We multiply the exponent down and subtract 1 from the exponent. So we have 2t to the first power. And the derivative of 3 is 0 because 3 is a constant, and the derivative of all constants is 0. So dx dt is just 2t. Now for y, dy dt will be equal to the derivative of 6t, and the derivative of a variable to the first power is just going to be equal to its coefficient, which in this case is 6, so dy dt is equal to 6. All right, so now we have dx dt is equal to 2t, and dy dt is equal to 6. Now we can plug those values into this formula, as well as g of t, our radius, to calculate the area of the surface of revolution formed by revolving the curve represented by these parametric equations around the x-axis between these two values of t. So let's set up our formula. the area will be equal to 2 pi times the integral from our lower bound of t to our upper bound of t. So that will be from 0 to 1. So we'll have 0 to 1 of g of t, our radius, which is 6t. So we'll have 6t times the square root of dx dt squared plus dy dt squared. So we'll have the square root of dx dt squared, and dx dt is 2t, so we'll have 2t squared plus dy dt squared, and dy dt is 6, so we'll have 6 squared. And then don't forget dt. All right, and so now we have set up our integral to calculate the area of the surface of revolution. Now all we have to do is simplify it and then solve it. Okay, so the first thing I'm going to do here is square both of these values underneath this square root. So we'll have that this is equal to 2 pi times the integral from 0 to 1 of 6t times the square root of 2t squared. We'll square each of those parts. 2 squared is 4, and t squared is t squared. So we'll have 4t squared plus 6 squared, which is 36. So we'll have 36, and then dt. All right, now if we want to simplify further, the next thing I'm going to do is pull this 6 out to the front. It's just a constant, so we can pull that outside of the integral, and 6 times 2 pi will be 12 pi. So this is equal to 12 pi times the integral from 0 to 1 of t times the square root of 4t squared plus 36. Now I do notice that both of these terms have a common factor of 4, right? We can pull 4 out of 4t squared and 36. 4t squared divided by 4 will be 1t squared, and 36 divided by 4 is 9. So we'll have 4 times t squared plus 9 dt. So we pulled 4 out of both of those terms, and now we can take the square root of each of these parts separately, and the square root of 4 is 2, so this will be equal to 12 pi times the integral from 0 to 1 of t times 2 times the square root of t squared plus 9 dt, right? We took the square root of 4, which gave us 2, and we took the square root of this quantity, so we have the square root of t squared plus 9, and then dt. Okay, so now we can simplify this a little bit further. We can move this 2 out to the front of the integral by multiplying 2 by 12 pi, right? 2 is just a constant, so we can pull that out to the front of the integral, and 2 times 12 pi will be 24 pi, so this is equal to 24 pi times the integral from 0 to 1 of t times the square root of t squared plus 9 dt. All right, and now at this point our integral has been simplified to its simplest form. There's nothing that we can really do to make it any simpler, and so now we should try to figure out what integration rule can we use to solve this integral. Now in this case I notice we have a composite function. We have the square root of t squared plus 9, and so it has an outside and inside function. The outside function is the square root function, and the inside is t squared plus 9. And whenever you have a composite function, it's probably a good idea to first see if you can use u substitution in any way. And when you want to use u substitution, you typically want to set the inside function of your composite function equal to u. But that's only going to work if whatever you set equal to u, its derivative is also within the integral. And in this case, that's actually true. Because if we set this inside function equal to u, right, t squared plus 9, the derivative of t squared is going to be a function of t to the first power. And that's exactly what we have on the outside of that square root function. We have t to the first power within our integral. All right, so what we can do here is use u substitution because we see a function and its derivative. So if we let u equal t squared plus 9, the derivative of that du dt will be equal to 2t, because the derivative of t squared, if we use the power rule for derivatives, will be 2t. We multiply that 2 down and subtract 1 from the exponent. And then the derivative of 9 is 0 because 9 is a constant and the derivative of a constant is 0. So du dt is equal to 2t. Now if we solve for du by multiplying both sides by dt, we'll have that du is equal to 2t dt. And now whatever du is equal to, we need to be able to find that in our integral so that we can replace it with du to rewrite the integral in terms of u. But in this case, I don't see 2t dt, I just see t times dt. All right, and so what we can do is just divide both sides by 2, and we'll have that du divided by 2 is equal to t dt. And now we can replace t dt with du divided by 2, and t squared plus 9 with u, and our integral will be in terms of u, except for the bounds of integration, which we will work on in just a second. But let's rewrite what we have so far. This integral will be equal to 24 pi times the integral from t equals 0 to t equals 1 of the square root of u times du divided by 2, right? We replace t squared plus 9 with u because that's what we set it equal to, and we replace t dt with du divided by 2 because that is what that is equal to. All right, now our bounds of integration are still in terms of t. That's why I wrote t equals 0 and t equals 1, so we don't forget that they are values of t, but we can easily change them to be values of u by plugging each of these values into what we set u equal to. U is equal to t squared plus 9, so when t is 1, we'll have 1 squared plus 9. 1 squared is 1 plus 9 is 10. So that upper bound will become u equals 10. So we'll have u equals 10. And then this lower bound, t equals 0, when t equals 0, we'll have 0 squared plus 9, which is 0 plus 9. And so u will be equal to 9 when t is 0. So we replace t equals 0 with u equals 9. Okay, and so now our integral is entirely in terms of u, so we don't have to worry about converting it back into terms of t. We can just integrate with respect to u, and then evaluate at our bounds of integration. And that will give us the area of the surface of revolution. And so now let's work on solving this integral. First thing that we can do is pull this 1/2 to the outside of the integral. And so we'll have 1/2 times 24 pi. So really we're just dividing this by 2. And so that will give us 12 pi times the integral from 9 to 10 of the square root of u du. But the square root of u, we can rewrite that to be u to the 1/2 power. That's the same thing as the square root of u. And so that will make it easier for us to see how to integrate using the power rule for integration. And so we'll have u to the 1/2 power times du. Okay, so now we can integrate with respect to u. Let's use the power rule of integration. We add 1 to the exponent and then divide by that new exponent. So this is equal to 12 pi times u to the 3/2 power, because 1/2 plus 1 is 3/2, and then we will divide by that new power of 3/2. And this is evaluated from 9 to 10. All right, so if we continue our evaluation over here, we can simplify it by remembering that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So instead of dividing by 3/2, we can multiply by 2/3. So this will be equal to 12 pi times 2/3 times u to the 3/2 power, evaluated from 9 to 10. But now I'm going to pull this 2/3 out to the outside so that we can just focus on evaluating u to the 3/2 power at 10 and then subtracting the evaluation at 9. So we'll have 12 pi times 2/3. That will be equal to 24 pi divided by 3, right? 12 times 2 is 24. And then we still have pi in the numerator and 3 in the denominator. But 24 divided by 3 is 8. So really, we can rewrite 24 pi divided by 3 to be 8 pi. And that will be multiplied by u to the 3/2 power, evaluated from 9 to 10. Okay, so now let's evaluate this at 10 and subtract the evaluation at 9. This will be equal to 8 pi times 10 to the 3/2 power minus 9 to the 3/2 power. All right, now the 3/2 power, that's the same as squaring our value and then taking the cubed root of it. That's not going to help us simplify 10 to the 3/2 power. That won't simplify nicely, but 9 will simplify nicely because if we rewrite it the way I said, we take 9 to the 1/2 power or take the square root of it and then cube it, that's going to simplify nicely. All right, and this is the same thing because if we were to simplify this, you would multiply these exponents, right? When you have a value raised to an exponent and that's raised to an exponent, you can simplify by multiplying those exponents. So 1/2 times 3 is 3/2. So this is the same thing. And 9 to the 1/2 power, or the square root of 9, is 3. And so we have 3 cubed, and 3 cubed is 27. And so this is equal to 8 pi times 10 to the 3/2 power minus 27. Okay, and so this is our exact value. There's nothing else that we can do to simplify this or make it look nicer, but this would be the exact value of the area of our surface of revolution. But if you want to get a better idea of what the actual value is, you can plug this into your calculator and find that it is approximately equal to 116.18 and some more decimals. And so what we found here is the area of the surface of revolution formed by revolving the curve represented by these parametric equations between these two values of t around the x-axis. Okay, so either of these answers is correct. Whether you have the exact answer or the approximate answer, they both represent the area of that surface of revolution. Okay, and so that was an example where we are revolving around the x-axis. Now let's look at an example where we are revolving around the y-axis. So here's our second example. We want to find the area of the surface formed by revolving the curve represented by the parametric equations around the y-axis. This time we have x equals 3 times sine t and y equals 3 times cosine t for the values of t from t equals 0 to t equals pi divided by 3. Alright, so this time, our surface of revolution that we want to calculate the area of is formed by revolving the curve around the y-axis. So we're going to use a slightly different formula because now the radius is going to be different. In this case, we will use this formula, which is exactly the same as the last formula for when we revolve around the x-axis, except the radius is now small f of t, not g of t. So the radius will be equal to what x is equal to in terms of t, because small f of t is the function that represents x in terms of t. So let's write that down first. Small f of t is equal to 3 times sine t. Okay, so that's the first thing that we can make a note of here. Now let's find the other two values that we need to set up this integral. We need dx dt and dy dt, which are the derivatives with respect to t of our parametric equations. And so let's find those. dx dt will be equal to the derivative of 3 times sine t, and the derivative of sine is cosine, so dx dt will be 3 cosine t, and then dy dt will be equal to the derivative of 3 times cosine t, and the derivative of cosine is negative sine, so we'll have negative 3 sine t. Okay, so now we have dx dt, dy dt, and small f of t that we can plug into this formula to set up an integral that will calculate the area of our surface of revolution, which is formed by revolving the curve around the y-axis. All right, so we're going to have s is equal to 2 pi times the integral from our lower bound of t to our upper bound of t. In this case, that will be from 0 to pi divided by 3. So we'll have 0 to pi divided by 3. And then inside the integral, we have small f of t, which is 3 times sine t. So we'll have 3 times sine t times the square root of dx dt squared plus dy dt squared. So dx dt is 3 cosine t and dy dt is negative 3 sine t. So we will have 3 times cosine t squared plus negative 3 sine t squared dt. Okay, so now we have set up our integral that will calculate the area of our surface of revolution. Now all we have to do is simplify the integral and then solve it. And so the first thing that we can do to simplify this is pull this 3 to the outside of the integral. We'll have 3 times 2 pi, which will be 6 pi. So this will be equal to 6 pi times the integral from 0 to pi divided by 3 of sine t times the square root of 3 cosine t squared plus negative 3 sine t squared. Now I'm going to square each of these values. And so 3 squared is 9, and cosine t squared will be cosine squared t. So we'll have 9 times cosine squared t plus negative 3 sine t squared. Negative 3 squared is 9, and sine t squared is sine squared t. So we'll have 9 times sine squared t dt. All right, and now to simplify further, notice that each of these terms underneath the square root have a common factor of 9, right? We can pull a 9 out of each of these terms. We have 9 times cosine squared t and 9 times sine squared t. So if we do that, this will be equal to 6 pi times the integral from 0 to pi divided by 3 of sine t times the square root of 9 times cosine squared t plus sine squared t. And now what we can do is take the square root of each of these parts. We can take the square root of 9 and the square root of cosine squared t plus sine squared t. And the square root of 9 is 3. And so what we'll have is that this is equal to 6 pi times the integral from 0 to pi divided by 3 of sine t times 3 times the square root of cosine squared t plus sine squared t dt. All right, so the square root of 9 is 3, and then we have the square root of these two terms right here. All right, now the next thing that we can do is pull that 3 to the outside. We'll have 3 times 6 pi, right? We can always pull out a constant to the front of the integral. So this will be equal to 18 pi times the integral from 0 to pi divided by 3 of sine t times the square root of cosine squared t plus sine squared t. And then don't forget dt. All right, now at this point it may seem like there's nothing else that we can simplify in this integral. However, there is one really nice thing that we can do here. If you notice, underneath this square root, we have cosine squared t plus sine squared t. We can rewrite that using one of our identities for sine and cosine. In particular, we can use the Pythagorean identity. And that identity looks like this: cosine squared t plus sine squared t is equal to 1. So we can replace cosine squared t plus sine squared t with 1 and just have the square root of 1. And so if we do that, this will be equal to 18 pi times the integral from 0 to pi divided by 3 of sine t times the square root of 1 dt, but the square root of 1 is just 1, and so we're multiplying sine t times 1, which is just sine t. And so this is equal to 18 pi times the integral from 0 to pi divided by 3 of sine t dt. And so by using this Pythagorean identity, we were able to simplify what looked to be a very complicated integral into a very basic and simple integral that we know how to solve pretty easily, right? We know that the integral of sine is negative cosine. And so let's work on that step next. This will be equal to 18 pi times negative cosine t evaluated from 0 to pi divided by 3. All right, the integral of sine t is negative cosine t, and we evaluate that at our bounds of integration. And so now what we want to do is evaluate negative cosine t at pi divided by 3 and subtract the evaluation at 0. So this will be equal to 18 pi times negative cosine of pi divided by 3 minus negative cosine of 0. All right, now cosine of pi divided by 3, that's equal to 1/2. So if we continue our work up here, this is equal to 18 pi times negative 1/2, right? We have that negative out front of the cosine function. So we have negative cosine of pi divided by 3, which turns out to be negative 1/2. And then we are subtracting negative cosine of 0, but those two negatives will cancel out. So we'll have plus cosine of 0, and cosine of 0 is 1. So we have negative 1/2 plus 1, and negative 1/2 plus 1 will be positive 1/2. So this is equal to 18 pi times positive 1/2, and 18 times 1/2 is 9, and so this is equal to 9 pi. And so 9 pi is the area of the surface of revolution formed by revolving the curve represented by these parametric equations between these two values of t around the y-axis. Okay, and so with that, this was the last example for this lesson video, but if you want to see some more examples, feel free to check out my examples video that I'll have linked at the end of this video, as well as in the description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.